Dr. M.C. Sundaraja. He completed his undergraduate studies from Madurai Kamaraj University and went on to complete his Masters in Structural Engineering from the same. He is a doctorate from Anna University and he has also done his postdoctoral fellowship at the Queensland University of Technology, Australia. He has more than 17 years of experience in the teaching profession and he has also published papers in 39 international journals, 7 national journals, 27 international conferences and 51 national conferences. He has so far published 124 papers in various journals. He went on to receive the Best Research Paper Award from IFERP, a unit of VVERT and NIRE on 4th April 2015. He has also received Outstanding Faculty Award from the Venus International Foundation Faculty Award, VIFFA, in the year 2015. Currently, Dr. M.C. Sundaraja is now working as an assistant professor in Tyagarajar College of Engineering, Madurai.
Welcome to UGC lecture series in B Architecture. Now we are going to have a lecture 2 in the unit 1. In the unit 1 we are having design of concrete members and working stress design of beams. And in the lecture 1 we have seen so far what do you mean by concrete, what do you mean by reinforced cement concrete, what are the reasons for using steel as a reinforcing material in the case of reinforced cement concrete structures, what are the grades of concrete, how to calculate amount of water for the particular batch of concrete, and also we have started discussing about what are the various methods of design of reinforced concrete elements. That is one is working stress design method, second one is ultimate load design method, third one is limit state design method. So far we have seen working stress design method and ultimate load design method. In the case of working stress design method, they consider only the concrete and steel as an elastic material. On the contrary, it is not a correct. That is, the concrete is a more complex material. The first, the disadvantages of working stress method, and the second one is in the case of working stress method, they have used huge amount of factor of safety for concrete and steel. Though they could design up to their working stress method, they have used huge amount of factor of safety. Since there are 3 for concrete and 1.8 for steel, the design will be safe, but it leads to uneconomical. And also the stresses developed in the structure, that is the actual stresses developed in the structures, is very much less than the theoretical values. So the assumption, that is the reason is that there are assumptions, that is the concrete is an elastic material, it is not correct. On the contrary, complex material is more complex materials. Next to that, we have seen the ultimate load design method. In the case of ultimate load design method, they have used taking the inelastic or plastic behavior of concrete and steel, and they have calculated the ultimate load by using the factor of safety, and the ultimate stresses are known real values. And also that in the case of ultimate load design method, though they have used the factor of safety to find out the ultimate load, the deflection and cracking effects were not considered. So this method is only used to find out the ultimate load after designing with the help of working stress method, which is used to calculate the factor of safety. So next, the rational and practical design method which was found, that is called as limit state method. This limit state method which overcomes the drawbacks of working stress method and ultimate load design method. So in the case of working stress method, they have designed only up to their working stresses. So they have used more amount of factor of safety, and also they have consider the concrete as an elastic material. On the contrary, it is not a correct, it is a more complex material. But and also in the case of ultimate load design method, they started considering inelastic and plastic behavior of concrete and steel. They have found ultimate load by multiplying with the factor of safety, and also the ultimate stresses are known real values, though they have used the deflection, or however the deflection and cracking effects were not considered. So this method, that is the ultimate load method, was only used to calculate and the ultimate load after designing with the help of the working stress method, which is used to find out the real factor of safety. So when you overcome the drawbacks of those two methods, the rational and practical method was found, that is called as the limit state method. In the case of limit state method, what do you mean by a limit state? And in the case of lecture 2, the contents of the lecture 2, which consists of methods of design of RC elements. So far in the lecture 1 we have seen working stress method and the ultimate load design method. In the schedule 2 we are going to discuss about a limit state design method. Next one is we are going to start the working stress method of design of structures. In the working stress method of design of structures, we are going to have what are the assumptions which are made in the concepts of design of the working stress method, and we are going to start analyze the rectangular section, and I am going to design the rectangular section using the equation which are or the expression which are found in the case of analysis of rectangular section. I have already told you that it is a rational and practical design method, that is a limit state method. It gives a new approach of statistical probability. What do you mean by limit state? That limit state means an acceptable limit for safety and serviceability of the structure before failure occurs. So, this is called as a limit state, an acceptable limit for safety and serviceability of the structures before failure occurs. So, there is a concept of design with such limit state is to achieve the acceptable probabilities, so that structure will not become unfit for use and will not reach the limit state. So, though this structures or RCC elements can be designed to their ultimate loading conditions, they have added certain factor of safety that is called as a partial safety factor. So, once the structure which has been designed to their ultimate load, it start failing when it reaches, when the stresses in materials which reach their respective ultimate stress conditions, it starts failuring. So, once in order to avoid that failure of structure, they have added certain factor of safety that is called as a partial safety factor. The partial safety factor, here it is, that is 1.5 for concrete and 1.15 for steel. This is called as partial safety factor. It is not like in the case of working stress method. Working stress method, the elements are designed to their working stress conditions. When they are not designed to their ultimate loading conditions, when you take the factor of safety, the factor of safety was found in the case of working stress method is 3 for concrete and 1.8 for steel. So, they have used huge amount of factor of safety, that is why this method failed. So, though the structures are safe after designing with the help of working stress method, this method will leads to uneconomical. So, this method, that is the limit state method, they design the structure to reach the stresses of the material to their ultimate loading conditions. In order to avoid the failure of the structures when it reaches the ultimate loading conditions, they are adding the factor of safety, that is called as partial safety factor. They are adding factor of safety partially, that is 1.5 for concrete and 1.8 for steel. So, in the case of limit state methods, there is a limit state means the acceptable limit for safety and serviceability of the structure before failure occurs. So, that is the concept of design with such a limit state to achieve an acceptable limit for safety and serviceability of the structures, so that the structure will not become unfit for use and will not reach the limit state. So, in the case of limit state design method, they have used two limit state, one is limit state of collapse and limit state of serviceability. That is, in the case of limit state method, they have added limit state of serviceability, that is the deflection and cracking effects were considered in the case of limit state method. So, here the statistical probability of strength and load can be estimated, which will be a limiting state of material in the case of limit state method, and the partial safety factor, that is I have already told you that the partial safety factor were introduced to reduce the probability of the failure to 0. That is in the case of limit state method. So, the advantages of limit state method over other method is, though this structure which is designed to their ultimate loading conditions, they have added some partial safety factor, that is 1.5 for concrete and 1.15 for steel. So, the structure will not be that is a probability of the failure of the structure in the case of limit state method will be reduced to 0. In addition to that, in the case of working stress method or in the case of ultimate load design method, the deflection and cracking effects were not considered, but here in the case of limit state method, the deflection and cracking were considered. These are all certain advantages and over the other two previous methods. Now, we are going to have a detailed look on working stress method. Before designing working stress method, we need to know what are the assumptions which are made in the case of working stress method. So, each and every method which has their own assumptions, and finally, they are checking that their assumptions are correct or not, and finally, they frame their assumptions. So, in the case of working stress method also they made certain assumptions. Using these assumptions only, the structures will be analyzed. Based on the analysis and the expression derived, they started designing the RCC elements. So, here the first assumption is at any cross section, the plane section before bending and remain plane after bending. What does it mean? It means that the strain at any cross section of the beam is directly proportional to the neutral axis. This is something like it is based on the theory of simple bending. In the case of theory of simple bending, the layers above the neutral layers are subjected to compressive stresses and the layers below the neutral layers are subjected to tensile stresses. That is, in the case of neutral layers, there is neither compression nor tension. So, when we move towards the top, the stresses are gradually increased. When we move towards the bottom, that is from the neutral layer, it is gradually increased and reaches the maximum value. So, the strain at any cross section of the beam is directly proportional to the distance from the neutral axis. This is the meaning of the first assumption, that is at any cross section, the plane section before bending remain plane after bending. The second assumption, all the tensile stresses are entirely taken care of by the reinforcement and none by the concrete except otherwise specifically permitted. This is a second assumption. So, here we all know that in the case of concrete, the concrete is very strong in compression, but weak in tension. So, in the case of a beam, when it is subject to any kind of force, if it is deformed, the layers above the neutral layers are subjected to compressive stresses. So, all the compressive stresses are entirely taken care of by concrete, since the concrete is very strong in compression. When you go below the neutral, that is a portion below the neutral layer, all these things are subjected to tensile stresses. So, here the concrete is very strong in compression, but very weak in tension. So, that is why we have provided an alternative material to resist those tensile stresses, that is the material which is called as a steel reinforcement. So, here all the tensile stresses are entirely taken care of by the steel reinforcement and none by the concrete except otherwise specifically. In some places, the concretes are allowed to take certain tensile stresses, that is in the case of water tanks. In some conditions, in some structures only, the concretes will be allowed to take some tensile stresses. Next one, third assumptions, the stress strain relationship of steel and concrete under working load is a straight line. The stress strain relationship of steel and concrete is a straight line. This is a stress and this is a strain. That is, they are taking as a linear one. It is considered as a linear. Stress is directly proportional to the strain. So, that is why they consider only up to this elastic limit, that is all. So, this is the point where the material reaches their maximum permissible value. So, that is why they have designed up to there. So, that is why the stress strain relationship of concrete and steel is under working load is considered as a straight line. Next, they have used, this is we have discussed already in the first schedule, that is modular ratio. That is a well known mechanics they have used in the case of working stress method. The modular ratio M is equal to 280 by 3 sigma CBC, where sigma CBC is compressive stress in concrete in bending, maximum compressive stress in concrete in bending. That is the bending stress. Again, the compressive stress, again it is called as a bending stress. So, where sigma CBC is a permissible compressive stress due to bending in concrete, which is represented in Newton per millimeter square, which is also given in table 21 of IS 456/2000. These are all the assumptions which is made in the case of working stress method. Based on these 4 assumptions, we are going to analyze and we are going to find out the expression to design the size of the section as well as the reinforcement required for it. First one, we are going to have, and there are 2 sections, one is rectangular sections, another one is flanged sections. We are going to analyze rectangular section and flanged sections are normally called as T beams or L beams. Now it is called as, now for example, in the case of a building which is supported like this, these are all the location of columns. How the slab systems can be provided for this one? The slab system can be provided or supported over the intermediate supports which is in the form of beam by connecting the column at the ends. So, here the slabs are supported on these supports. These supports are acting as when you take the cross section of the slab, this is a cross section of the slab which is supported over this beam and this beam, and here these are all called as the beam, and these intermediate beams are designed as T beams. It may be also be designed as a rectangular beam, but it is something like when you take the cross section, this portion is called as a flange portion or slab portion. The slab portion is called as a flange portion and this portion is called as web portion. So, these intermediate beams can be designed as a T beam, and these edge beams will be designed as a L beam. That is, it is something like an inverted letter L. So, that is why it is called as L beams. And now to the analysis and design of T and L beam are almost the same. Only the difference is the flange portion. In the case of T beam, the flange is on either side of the web portion, and in the case of L beam, the flange is on only one side. So, first we are going to have a analysis of rectangular sections. And before that, in the case of beams, there are three different sections. One is balanced section, second one is under reinforced section, third one is over reinforced section. What do you mean by balanced section? Balanced section means normally the reinforced concrete members are designed on the basic assumption that the stresses in concrete and steel reach their maximum permissible stresses at the same time. Both the materials are stressed to their maximum permissible value one and at the same time. That section is called as balanced section. For example, if we have a rectangular section, now this is taken as neutral axis of the beam. This is the neutral axis. Now, here you consider this as a singularity. Now, what do you mean by saying? I will explain later. Now, here if you take this as a stress diagram, so here the axis passes through the balanced section is called as balanced neutral axis or critical neutral axis. The depth of this critical neutral axis from the topmost extreme fiber to the neutral axis is called as taken as XC. That is, XC is the depth of balanced section you take. What do you mean by the balanced section? This is I already explained. That is, RCC members are designed on the basic assumption that the stresses in concrete and steel reach their maximum permissible stress values at the same time, or both the materials are stressed to their maximum permissible value one and the same time. That section is called as a balanced section, and the axis passes through the neutral layer, that is axis passes through the section is called as the balanced neutral axis or critical neutral axis, and the depth of the neutral axis is denoted by XC. XC is the depth of critical neutral axis, depth of critical neutral axis. So, here both the materials are stressed to their maximum permissible value one at the same time. So, that is sigma CBC and sigma ST. Now, in the case of other section, that is, now we move on to under reinforced section. If less steel, under reinforced means less steel. If less steel than that required for the balanced section is used, that is called as under reinforced section. In such condition, in this section, the steel is stressed to its maximum permissible value, while the concrete stressed below the maximum permissible value. So, here in the case of under reinforced section, since we are using less steel, the concrete area will become more. So, among these two material, we are using less amount of steel. So, when it is subjected to any kind of forces, the steel is subjected to steel reaches their maximum permissible value first. So, here when you take this stress diagram, so in such condition, what is the type of failure which occurs in the case of under reinforced section? Since the steel is stressed to their maximum permissible value, the section which fails due to over stress in steel initially. So, the type of failure which occurs in the case of under reinforced section is tension failure or ductile failure. Then what about the neutral axis of the under reinforced section? So, since it is an unbalanced section, the neutral axis is situated at the center of gravity of the section. My question is, the neutral axis whether moves upwards or downwards. Since we are using less amount of steel, the area of the concrete is almost more. So, automatically the neutral axis will be moved upwards. So, this is the neutral axis of the under reinforced section. So, I am taking x as the actual depth of neutral axis. So, since the neutral axis is situated at the CG of the section, the neutral axis moves upwards in the case of under reinforced section. So, when you compare this actual neutral axis with the critical neutral axis, in the case of under reinforced sections, x is less than xc. Once you find out the actual depth of a neutral axis, if it is compared with one another, if x is less than xc, the section will be under reinforced section. Now, we move on to over reinforced section. Now, in the case of over, so if more steel, over reinforced means more steel, if more steel than that required for the balance section is used, that section will be called as over reinforced section. In such condition, in this section, the concrete is stressed to its maximum permissible value first, while the steel is stressed below its maximum permissible value. So, here in the case of under reinforced section, steel is stressed to its maximum permissible value, while the concrete is stressed, that is actual CBC is less than the permissible CBC. In the case of over reinforced section, if we are here we are using more amount of steel, in the concrete area automatically reduced. So, among both the material, the concrete is stressed to its maximum permissible value first, while the steel which is stressed below its permissible value. So, what about the neutral axis in this? What about the failure of the over reinforced section? Since the concrete is stressed to its maximum permissible value first, the nature of failure occurs in the case of over reinforced section is sudden failure or brittle failure. Normally, concrete is why it is sudden? Since the concrete is it's a brittle material, it fails suddenly. It shows the it fails suddenly. So, here the nature of failure is brittle failure. What about the neutral axis? Since it is a unbalanced section, neutral is going to be situated at the center of gravity of the section. So, here in the case of over reinforced section, we are using more amount of steel, they automatically the neutral axis moves downwards. What about the depth of neutral axis? This is the depth of neutral axis for over reinforced section. Suppose when you compare x with xc, x is greater than xc. If x is greater than xc, it is called as over reinforced section. These are three important sections in the case of analysis of rectangular or any flanged section. Before analyzing any rectangular flanged section, we must thoroughly know the what do you mean by balanced section, what do you mean by under reinforced section, what do you mean by over reinforced section. I am repeating, in the case of balanced section, both the materials are stressed to their maximum permissible value at the same time, that is one and at the same time. That is why it is called as a balanced section. The axis passes through the section is called as balanced neutral axis or the critical neutral axis. The depth of neutral axis here it is called as xc. So, here the maximum stress at the topmost extreme fiber is sigma CBC, that is a permissible value, and here at the bottom is sigma ST, that is in the reinforcement it is sigma ST. What about the under reinforced section? Under reinforced means less steel used. If less steel than that required for the balance section is used, that is called as under reinforced section. In this section, the steel is stressed to its maximum permissible value first, while the concrete is stressed below the permissible value. So, under such condition, this section will fail initially due to over stress in steel. So, this type of failure which occurs in the case of under reinforced section is tension failure or ductile failure. What about the neutral axis? Since it is here it is an unbalanced section, automatically the neutral axis is going to be situated at the center of gravity of the section. Since we are using less steel, we are having more amount of concrete. So, the neutral axis which moves towards top, which moves towards the compression side. So, here we are taking x as the actual depth of the under reinforced section. When compared with xc, here x is very less than XC. If X is less than XC, we can conclude that it is under reinforced section. What about over reinforced? Or that is, if you are using more amount of steel, that is called as a over. So, more amount of steel than that required for the balance section is used, that section is called as over reinforced section. In this section, the concrete is stressed to its maximum permissible value, while the steel is stressed below its permissible value. Under such condition, this section will fail initially due to overstress in concrete. Then what about the neutral axis? Since automatically the neutral axis moves getting downwards. So, and you take x as the depth of the neutral axis and compare to XC, here x is greater than XC. If x is greater than XC, it is over reinforced section. Now, and these are all the three important sections before we need to analyze any rectangular or flanged section. So, here the three sections we have seen, and before that type of failures. Before that, before we conclude these three sections, what is the most important section among these three sections? What is the most safest section? So, I am saying that the most safest section is the under reinforced section. Most safest section is under reinforced section. The reason behind its nature of failure. The nature of failure here, it is tension failure or ductile failure. The tension failure or ductile failure which shows the failure, it will not fail suddenly, it is not a brittle in nature, it is a ductile in nature, it shows the failure, we can easily rehabilitate this section. So, the most safest section among these three sections is under reinforced section. So, in the case of limit state method, and we have talked about a limit state method, we are going to discuss about limit state method. Though these three sections are designed in the case of working stress method, in the case of limit state method, they are avoiding designing over reinforced section. Since its failure, the nature of failure is brittle failure. The brittle failure is a sudden failure, always called as it failed suddenly, it will not show the failure. So, we can't rehabilitate these structures, that is why they have avoided in designing over reinforced section in the case of limit state method. Let us summarize what we have discussed so far in the schedule 2. One is the method of design of RC elements. We have discussed the concepts of limit state method, and then what are the advantages of limit state method over other two methods, what are the factors of safety they have used in the case of limit state design method, and we have started discussing about working stress method in detail. In this one, we need to discuss about the analysis of rectangular section. Before analyzing that rectangular section, we have discussed about the three important sections, that is balance section, under reinforced section and over reinforced section. In these three sections, what about the neutral axis, what about the nature of failure of those sections, and also which section will be the most economical as well as most safest sections we have finalized. And with regard to the questions, so far we have discussed concept of limit state method. From that, I need to ask what is define the term limit state, and what are the advantages of limit state method over other two methods. This is more important question. And we have discussed three sections and differentiate between under reinforced and over reinforced section, and define the section, that is we have to define what you mean by under reinforced section, over reinforced section. And also next one is they explain the nature of failure of FO section. What are the nature of failure which occurs in the case of the balance section, under reinforced section and over reinforced section. And with regard to the references, we need to refer an IS 456 2000 plain and reinforced concrete code of practice, and also we can refer a well known book that written by S. N. Sinha, that is reinforced concrete design. With this, we come to the end of this lecture. Thank you.